We saw this simple two-link robot in the previous lecture about forward kinematics. The tooltip pose of this robot is described simply by two numbers, the coordinates x and y, with respect to the world coordinate frame. So the problem here is that given x and y, we want to determine the two joint angles q1 and q2. The solution that we're going to follow in this particular section is a geometric one. We're going to start with a simple piece of construction. We're going to overlay the red triangle on top of our robot. And we know that the endpoint coordinate is x, y, so the vertical height of the triangle is y, the horizontal width is x, and using Pythagoras' theorem we can write r squared equals x squared plus y squared. So far so easy. Now we're going to look at this triangle highlighted here in red, and we want to determine the angle alpha. In order to do that, we need to use the cosine rule. And if you're a little rusty on the cosine rule, here's a bit of a refresher. We have an arbitrary triangle. We don't have to have any right angles in it. And we're going to label the length of this edge as A, and the angle opposite that edge we're going to label as little a. And we do the same for this edge and this angle, and this edge and this angle. So altogether, the sides are labelled capitals A, B and C, and the angles are labelled little a, little b and little c. So the cosine rule is simply this relationship here. It's a bit like Pythagoras' theorem, except for this extra term on the end with the cos A in it. Now let's apply the cosine rule to the particular triangle we looked at a moment ago. It's pretty straightforward to write down this particular relationship. We can isolate the term cos alpha, which gives us the angle alpha that we are interested in, and it's defined in terms of the constant link lengths A1 and A2 and the position of the end effector x and y. We can write this simple relationship between the angles alpha and q2, and we know from the shape of the cosine function that cos of q2 must be equal to negative of cos alpha. This then lets us write an expression for the cosine of the joint angle q2. Now we're going to draw yet another red triangle, and we're going to apply some simple trigonometry here. If we know q2, then we know this length and this length of the red triangle. We can write this relationship for the sine of the joint angle q2. Now we can consider this bigger triangle, whose angle is beta, and the side length of the triangle is given here in blue, and the length of the other side of the triangle is this. So now we can write an expression for the angle beta in terms of these parameters here. Going back to the red triangle that we drew earlier, we can establish a relationship between q1 and the angle beta. Introduce yet another angle, this one gamma, and we can write a relationship between the angle gamma and the tool tip coordinates x and y. Now we can write a simple relationship between the angles that we've constructed, gamma and beta, and the joint angle we're interested in, which is q1. And the total relationship looks something like this. Quite a complex relationship. It gives us the angle of joint 1, that's q1, in terms of the end effector coordinates y and x, and a bunch of constants, a1 and a2, and it's also a function of the second joint angle q2. So let's summarize what it is that we have derived here. We have an expression for the cosine of q2, and we have an expression for q1. Now, the cosine function is symmetrical about 0. So if we know the value of the cosine of q2, then there are two possible solutions, a positive angle and a negative angle. We're going to explicitly choose the positive angle, which means that I can write this expression here. And now we have what we call the inverse kinematic solution for this two-link robot. We have an expression for the two joint angles, q1 and q2, in terms of the end effector pose, x and y, and a bunch of constants. You notice that the two equations are not independent. The equation for q1, in fact, depends on the solution for q2. In this case, q2 is negative, and we're going to write the solution for q2 with a negative sign in front of the inverse cosine. Now we need to solve for q1, so we're going to introduce this particular red triangle, the angle beta that we saw previously, and the angle gamma, which is defined in terms of y and x. Now we write a slightly different relationship between q1, gamma and beta, different to what we had before. There's a change of sign involved. Then we can substitute all of our previous equations and come up with this expression for q1. Again, there is a change of sign here. Previously, this was a negative sign. And here in summary form is the solution for the inverse kinematics of our two-link robot when it is in this particular configuration where Q2 is negative. Let's compare the two solutions, the case where Q2 is positive and the case where Q2 is negative.